Okay, so we're starting a brand new unit today, so therefore it's going to be a different part of the work booklet. Experimental probabilities is going to be the name of the game today. Here we go. So we start a new chapter today, probability and odds. That's what the whole chapter is going to be on. We're starting with probability, of course. We have a few key focuses for today. We're going to look at understanding the relationship between fractions, decimals, and percentages. That's not going to take us very long. That's entirely review. We're going to understand the meaning of probability. We're going to talk about how to calculate the experimental probability as well as what that means. And then we're going to have a very brief discussion on the importance of a proper sample size and sample type. We'll get into that in a little bit. Well, let's get rolling. So fractions, decimals, and percentages, again, this is review. I imagine you probably already know this because we've kind of already used this, especially in our last chapter on statistics. But I want you to recall that fractions, decimals, and percentages are all inherently linked. Fractions can be turned into decimals by dividing the numerator, that's the top number, by the denominator. Decimals can be turned into fractions most easily by writing it as a numerator over an appropriate base 10 number, like 10, 100, 1,000, etc. Basically, to do this one, in case you're not aware, is if it's a number that's to the 100th place, so for example, like 0.25, you're going to write that as something over 100 because this is the 100th place, so you'd say it's 25 over 100. You can simplify your fraction down from there, like you say, well, both these numbers are going to divide by 5, for instance, but again, we won't worry about that for now. Next up, percentages are the decimal representation multiplied by 100. So in other words, if you have decimals, you pretty much already have percentages. And we did see that in the last unit on statistics, especially when we dealt with percentiles. That was very similar to percentages, of course, but still the same idea. So I found this picture. I just quickly Googled this and found this. It's pretty clear, I think. Again, a fraction is a numerator and a denominator. If you went 3 divided by 10, you get 0.3. And then again, if you took your decimal and times it by 100, you get 30%, right? So that's a relationship that exists between all three of those. The reason this is important is because probability is going to be represented as any of these three. Probabilities can be percentages, fractions, or decimals. So we need to know that these three things are connected because sometimes it's nicer to have one over the other. So speaking of probability, a probability is just the chance of a certain event happening, right? Just how likely something is to happen. That's probability, right? So probabilities, as I mentioned just a minute ago, can be expressed as either a fraction, a decimal, or as a percentage. Most people, just in terms of spoken conversation, seem to prefer percentages. But in terms of actually calculating probabilities, we're almost always going to be dealing with fractions. But it is important to know how to change it to a decimal or as a percentage because sometimes you'll be asked to do so. So the probability of an event A happening is denoted by PA. So when you see something like this, P and then in brackets A, that means the probability of A happening, where A is just whatever event you have, right? So if you said A is the likelihood or the probability of rolling a 2 when you roll a dice, then that would be the probability of rolling a 2. Matter of fact, you'd even just probably just say P2 instead of using the letter A. You can use whatever you want in there. We're just saying it's event A. Now, generally speaking, the probability can be calculated using this formula. P of A, so the probability of A happening, is the number of occurrences of event A divided by the total number of possible outcomes. So in other words, the number of times that A kind of happens divided by the total number of things that could happen. That is how you find a probability, generally speaking. That's about as simple as it gets. This is on your formula sheet. If you want it put in a little bit more of a simple term, you could say it's how common A is divided by the total possible outcomes. If this formula looks a little fishy to you, I don't blame you actually, because it is kind of vague with how, how it's worded, but it's much easier to understand with an example, which is what we're going to get to right now. So for an example, suppose in a sock drawer there are 2 red socks, 3 green socks, 8 white socks, and 6 black socks. What is the probability of randomly picking a red sock? So in other words, you close your eyes and you put your hand in the sock drawer and pull one sock out. What's the probability of just randomly picking a red sock? Express this as a fraction, a decimal rounded to the nearest hundredth, and as a percent rounded to the nearest whole percent. Well, on that last slide, I'll just bounce back to it real quick. We can see that the probability of something happening, probability of A happening, is the number of occurrences of event A divided by the total number of possible outcomes. The total number of outcomes is going to include the occurrences of event A in the first place. It's the whole big grand total. So here's how this can apply here. If we're going to talk about finding it as a fraction, well, that's where we're going to start with that formula on the last page. So we're going to say the probability of, I could call it A, but you know what, instead I'll call it P red See, like it's really flexible here. You can be as flexible as you wish with this. So I'll say P red equals the number of occurrences of red sock. Well, if you look at the number of occurrences of red sock, there are 2 red socks in this drawer. So we'll say 2 over the total possible number, right? Well, the total possible number is going to be all these socks combined because they're all in that one sock drawer. So we're going to have 2 plus 3 plus 8 plus 6. Well, 2 plus 3 is 5, 5 plus 8 is 13, 13 plus 6 is 19, so 19 total possible outcomes. So 2 over 19. That right there is one of your answers. Your probability of picking a red sock is 2 out of 19. 2 out of 19 is your probability expressed as a fraction. Next up, though, it wants it as a decimal. Well, to turn a fraction to a decimal, we just need to divide that numerator by the denominator. So if I just get my calculator out real quick here, we can also say that P red, probability of picking a red sock, is 2 divided by 19, which to the nearest hundredth is 0.11. That would be another way of expressing this probability. So again, probabilities could be a fraction, but they could also be a decimal. Now, additionally, it wants us to write it as a percentage. Once you have the decimal, getting a percentage is pretty easy. You just times your decimal by 100. So then we can say P red as a percentage now is 0.11 times by 100, or in other words, just 11%. This is what I was kind of getting at earlier on. In just spoken language, people really like probabilities expressed as a percentage. It just really jives well with how our brains work. It's nice to hear, oh, the probability of picking a red sock from the store is 11%. It's just a really good way that our minds like hearing. But again, fraction is usually how we start this. So 2 out of 19, and that's pretty nice for our mind as well. 2 out of 19 is a good way of thinking of it. Decimals are useful for calculations, which we might get to later on, but in terms of expressing it to another person, percentages are pretty good, right? Percentages are quite nice to understand, 11%. So moving on now to experimental probability. The probability of an event happening isn't always possible to directly calculate without doing an experiment first. In that last question, we knew what socks were in that drawer, right? So we could find the probability of picking a red sock. There's no arguing on that one, right? But if we didn't know all the parameters and we had to do an experiment, then what we're actually finding is called an experimental probability. So if an experiment is done and the data from that experiment is recorded, this can be used to calculate the experimental probability. This is the same idea. It's the number of times that you saw event A happening divided by the total number of outcomes you had in the first place, right? So again, like I just wrote below, tells you the number of times event A occurred out of a total number of trials performed. So the experimental probability can change from one experiment to the next, right? So in other words, if you did an experiment and you found an experimental probability of, let's say, pulling out a red sock from a drawer, and then you restarted the whole thing and did it again, you might get a different experimental probability the next time you did it. And that's okay. Now, just ideally though, if you did a very large number of trials, so in other words, if you kept pulling socks out of a drawer and then putting them back and pulling the sock out again, like if you did that 1,000,000 times, your experimental probability would probably closely match the true probability of event A occurring. So in other words, the bigger your trials, the more trials you do, the more accurate your experimental probability will be, generally speaking. We'll do a really simple example. Again, it's going to be another sock example. Suppose this time you had a mystery sock drawer, not the same sock drawer as before. You reached into the drawer and pulled out one sock at a time. In your experiment, you pulled out 4 green socks, 7 red socks, 5 white socks, and 11 black socks. Find the experimental probability of pulling out a green sock expressed as a fraction, a decimal, and a percentage. This really is the same thing as what we did before. All that's different is we're doing an experiment instead of knowing what's going on. So if this is looking like it's the exact same question we had before, just in different numbers, that's because it is, right? So again, if we're looking for an experimental probability of a green sock, we can say P green equals the number of successful outcomes. Well, successful here is green in this case, so we'll say 4, divided by the total number of outcomes. Well, that would be 4 plus 7 plus 5 plus 11. So 4 plus 7 plus 5 plus 11. Adding this all together, 4 plus 7 is 11. 11 plus 5 is 16. 16 plus 11 is 27. So there's 27 different trials we did here. So 4 out of 27 would be our probability expressed as a fraction. Now, again, we also want to list this as a decimal. It didn't tell us to round this time, but I will anyway. Rounding to the nearest hundredth is usually just good measure. So P green is going to equal 4 divided by 27, which is about, if I round to the nearest hundredth, 0.15. So 0.15 would be the probability of picking a green sock in this case. Now, last one, of course, percentage, you just take your decimal and times it by 100. So P green is going to equal 0.15 times 100, which is just 15%, which again is a really nice way of expressing a probability. We really like hearing percentages. So the experimental probability here is 15% or 0.15 or 4 out of 27. If you were to restart this trial and do it over again, you might actually get a different number. This is just your probability from an experiment that you did. If you did this experiment again and pulled out like 1,000 socks, you get a pretty accurate look at what the probability of pulling a green sock out of that drawer would be, right? Anyway, moving on. Samples. A sample is the collection of events/objects being observed. So in other words, it's what you're actually like looking at. It's what you're actually doing your experiment with. Now, both the size and the type of your sample are important to consider. So here's just two situations, and I want you to think about it, and then I'll reveal what I think about it afterwards. So if you want to pause after I finish reading this, you can, just to think about it. But suppose you were in charge in ordering lunch for 100 people. The options are pizza, tacos, or Chinese food. You can't order individually for each person. Everybody's going to get the same lunch. You asked 5 of the people what to order. There's your sample, 5 people. 5 out of the 100 people you're ordering food for. You asked 5 people what to order. What's wrong with your sample choice? You can pause here and think about it, and then I'll tell you. So what I think is wrong with the sample choice, I think it's, you know, pretty clear. If you got 100 people to order lunch for and you're only asking 5 of them what they want, your issue with your sample choice is it's too small, right? Your sample should have been a lot bigger in this case. As a matter of fact, I think if you're ordering lunch for 100 people, you might as well go out and ask all 100 of those people. But at very least, you should ask a good percentage of those 100 people what they would want. So even if you asked half of them, what do you guys want for lunch? Then you took the winning option. That would probably be a pretty safe bet. But asking only 5 people, that's not going to give you a very good indication of what all 100 of those people would want. So again, you have too small of a sample in this case. Next one, suppose you want to find the probability of a Canadian citizen having their own YouTube channel. You call the local seniors home to conduct your survey. What's wrong with your sample in this case? You want to pause and think about it, and I'll go over it. So this one is a little bit weird, and we're making a lot of assumptions on this one. But what I would say what's wrong with your sample is the sample type is wrong. You're asking the wrong group of people. I don't mean to be rude on that one. What I'm really saying is here, generally speaking, you can imagine your people in a seniors home, they're going to be a lot less likely than your average Canadian to actually have their own YouTube channel. Many people who are in seniors homes might not even use computers, for instance. I know my grandpa, for instance, he certainly has never used a computer at all, and he's in a seniors home, right? So you're asking the wrong group of people. If you wanted to find for all Canadian citizens, how many people have their own YouTube channel, or at least the probability that someone has a YouTube channel, you'll want to ask a whole bunch of different people. You're not just going to ask elderly people. You'll ask elderly people, middle-aged people, young people, etc. Right? You're gonna have a more broad type of sample than just asking one specific type of people here. So I would just say you're asking the wrong group of people, or at very least too narrow of a group of people. You need a more diverse group of people to be asking a question like that too, right? Anyway, we're done for some practice. I want you to go through your work booklet, and I want you to work on page 146 to 153. Again, we are in a new chapter now. Get as many of those questions done as you can. There are some that aren't actually in that actual, what do they call it here, the practice your skills part. There's some of the other ones that are just kind of buried between their examples. I want you to give those a try too, at very least, okay? Anyway, as usual, if you have any questions, please send me an email or send me a remind, whatever you need. Best of luck.